and we have 1, 2, 3, 4, 5, 6, 7 slides to end. In the last subsection, we are looking at inverse linear transformations. We want to look at inverse linear transformations, and we see with this linear transformation, just like we said, to start with, for starters, they are functions, and we know for any function, even when we are studying functions in senior 3 mathematics, or some of you who are teaching, who are involved actively in teaching, when you're teaching functions, then you know that those functions, you can get inverses for those functions. So we want to look at the inverses for the linear transformations. And we start with a linear transformation T, which takes V to W, and the range of T. Then the range of T, which is denoted by RT, we saw that that range is a subspace of W. It is a subspace of W consisting of all images under T. We define the range as a set of all those elements which are images of some elements in V. So the range is a set of all images under T or vectors in V. Now, if T is 1 to 1, we know what it means for a function to be 1 to 1 from Curriculus 1, which was the very first course we studied in year 1. So 1 to 1, if T is 1 to 1, it means every vector in V is mapped to one and only one element in W. That is 1 to 1. So if T is a 1 to 1 transformation, then it means that each vector W in RT is an image of a unique vector, because 1 to 1-ness guarantees that every V is mapped to a unique image the other side. So it means this unique image is also an image of a unique vector this side. Now, the uniqueness allows us to define a new function which we call the inverse. The uniqueness means we can define a function which maps the range back the other side, which we call the inverse, and that one will map the image elements in the range back to V. And it can be proved that this new transformation, which takes the range back to V, is a linear transformation. And it's a linear transformation, and moreover, we see that when we get T inverse of T of V, this is the same as T inverse of W, because T of V is an image of some V, and if we let that be W, then this is T inverse of W, and T inverse of W should take us back to V. So we define a linear transformation T taking V to W, then the T inverse will be taking the range of W back to V, so that one will be a linear transformation given by that. And from the theorem we saw, since T inverse is also a linear transformation, T inverse is also a linear transformation, then the composition gives us the identity transformation. So when we compose T followed by T inverse, it takes us to the identity in V, identity transformation in V. And T inverse followed by T, it takes us to the identity transformation in W, where I is the identity transformation. Okay, so that is the inverse of a linear transformation, and we want to have a look at an example. So the example, we have a transformation. It is a linear operator actually, because it is working within the same space, same vector space R3. So it takes things in R3, it returns R3. It is defined by give it a vector in R3. It multiplies the first entry by 3, it leaves the second, it adds the second entry minus twice the first entry minus 4 like this, and then so it returns okay, yeah, so this is it, this is 1, then this is 2, this is 3, so it is on R3. Determine whether this T is a 1-to-1, and if it is 1-to-1, determine T. Okay, so now we want to show that this linear transformation is 1-to-1 because it is the condition of being 1-to-1 that guarantees the existence of the inverse transformation. So now I want to ask a question. Who can tell us what we need to check in order for us to be sure that a given function is 1-to-1? What do we need to check to show that a function is 1-to-1?
I think we shall solve those equations, those 3 equations. Then if we get different,
we shall solve the 3 equations, equate them to what?
To 0. And if we get different answers, each having, if x1, x2, and x3 have different answers, then we shall know x1 is what? And 1-to-1.
If they have different answers?
Yeah, distinct answers.
Distinct. If they are distinct, then it is 1-to-1.
Yeah.
Okay, there's an idea in what you're saying, but you're not bringing out it clearly. Any other person? What do we need to check to be sure that a given transformation is linear? I mean, a given transformation is 1-to-1, okay. Let me take us to speed. From these vectors, like Dale said, we pick the standard matrix for this transformation. So here we form these as equations. This is 3, 1, 0. So we pick the coefficient matrix for those equations. This matrix is invertible. We check if this is the matrix for the transformation actually, because you can see that if I get that matrix, then times x times this vector here, I get this linear, this one. So if this matrix of transformation is invertible, then the given transformation is said to be 1-to-1. Okay, so we find the inverse of this. This matrix is invertible, verify. So you find the inverse. If you find that the inverse here exists, then this matrix is invertible. In fact, the inverse is given by that. So you prove that the inverse is this. Then it follows that the standard matrix is denoted by, which is T inverse. Here, it is given by T inverse. We know the properties of inverse. It is the same as that. So since we have the inverse, so since we have been able to find the inverse, it means this matrix, I mean this transformation is invertible and the inverse exists. And so since it is invertible, then it means it is a 1-to-1. It is a 1-to-1. It is a 1-to-1 transformation. Then the last part was asking us to find T inverse of this. So it means it is going to be T inverse of that. So we get this matrix. This is the matrix for the inverse transformation, and we multiply it by this vector. There's a step where there is T inverse here. We can put this matrix times this. So you see, this is 4x1 minus 2x2 minus 3x3, which is that, minus 11x1 plus 6. Yeah, so we get this matrix of the inverse transformation and we multiply it here. Okay, any questions? Any questions? Okay, silence means no. Okay, so we proceed. Inverse, we are looking at inverse. We said if T1 is a vector, is a linear transformation mapping vector space U to vector space V, T2 maps V to W, linear transformations, then this theorem says the composition is 1-to-1. And if it is 1-to-1, it means this composition, we saw from the previous theorem that this composition is also linear. And if it is linear, it is 1-to-1. That means this inverse exists, and the inverse is given by that. So this theorem can surely be proved, and we are going to go through the proof. So the proof, one, we want to show that this is now where the definition that we looked at in linear algebra 1 comes in. We let U1, U2 be two elements in U, such that this composition, such that their images are equal. Actually, to prove that the function is 1-to-1, then we need to check that if the images are equal, then their objects are also equal, because 1-to-1 requires that no element in the domain is mapped to more than one element in the range. So if I have two equal elements in the range, then that one should mean that even what I have in the domain are equal. So that is the uniqueness. Or alternatively, if I have things which are different in the domain, then it should give me things which are different in the domain. I think that's what Deus was trying to mean. That's what Deus was trying to tell us. So we let these